However, there is a completely different world close to us. Its depths shudder with devastating internal cataclysms, and hundreds of bubbling volcanoes unpredictably lash out at the space around with massive emissions. A huge planet covers most of its sky, occasionally eclipsing the dim sun, and its vast valleys are painted in millions of yellow-red hues. Such is Io, Jupiter's satellite, dangerous and fierce, but at the same time so beautiful and marvelous. More than 4 centuries ago, back in 1610, Galileo Galilei made one of the greatest astronomical discoveries of his time. Through his telescope, quite small by modern standards, he managed to make out 4 objects close to Jupiter. One of them was named Ganymede, and is now considered the largest satellite in the solar system. The other 2, Europa and Callisto, have proven to be promising candidates for the search for extraterrestrial life. The 4th satellite, located closest to the gas giant, was dubbed Io. For a long time, technical limitations have prevented us from seeing details of the surface of this celestial body, and its composition and internal structure remained a matter of conjecture. However, thanks to the advancement of science, astronomers have gained more and more information over time. Today, Io is known to be one of the largest satellites in the entire solar system, second only to Ganymede, Titan and Callisto in size. Its radius is 1,821 kilometers, and its mass reaches about 8.9 times 10 to the power of 22 kilograms. If we compare this celestial body with the Moon, it turns out that these objects are almost identical in size. However, if we compare the masses, we will notice that Io is more massive than the main satellite of our planet by as much as 21%. This suggests that the average density of this space object is higher than that of any other satellite in the solar system. According to calculations, it is about 3.5 grams per cubic centimeter, which is noticeably higher than most non-metallic rocks. And to understand the reasons for the anomalous density of Io, we need to look deep into it. According to today's concepts about the structure of celestial bodies, Io has a relatively compact core at its center, made up of iron and sulfur. It accounts for about 20% of the satellite's mass, and its radius, according to different estimates, is between 350 and 900 kilometers. Calculations show that given such parameters, internal heat release will be insufficient to melt most of the core. This is also confirmed by the fact that this celestial body has almost no magnetic field of its own. Mathematical modeling shows that the satellite's core is surrounded by a solid mantle, at least 75% of which is made up of the magnesium-bearing mineral forsterite. According to calculations, its outer part is molten and forms an ocean of magma about 50 kilometers deep. Its temperature is about 1600 Kelvin, which is more than 1300 degrees Celsius. Deeper layers are under high pressure, and therefore they retain a solid state even at extremely high temperatures. In its turn, the mantle is covered by the lithosphere, which is between 12 and 40 kilometers thick. Despite its considerable thickness, it is not monolithic. In some areas, the surface of the celestial body is cracked, forming large structures filled with lava. At the same time, spectral analysis shows that unlike with most satellites, there is virtually no water, ice or frozen gases on Io. The outer surface of the celestial body consists of basalt and sulfur for the most part. but also has flecks of other dense minerals. And this is exactly what accounts for its abnormally high density. And one of the most notable features is certainly the huge orange-brown ring located in the southeastern part of the satellite. This vast area extends for more than 1,000 kilometers and is comparable to a large African country in terms of its size. It is believed to be formed by deposition of sulfurous emissions from the ancient Pele volcano, which is located in the center of the ring. Analysis of photographs, taken both in the infrared and visible ranges, shows that in the center of the ring there is the patra of this volcano, which is a multi-level cavity reaching 30 by 20 kilometers, filled with lava. Incidentally, the temperature of the molten rock surface is distributed unevenly and constantly varies, reaching 1300 degrees Celsius at the hottest points. The patra is believed to be connected to the satellite's glowing mantle by an underground channel. The lava inside the rift is constantly stirring due to the fact that volatile substances dissolved in it try to rise upwards with a flow of molten rock following. Because of this, the thin crust of solidified matter covering the surface of the lake occasionally cracks and breaks, causing outbursts and lava ejections. Some of them can be upwards of 300 kilometers in height, sending solidified sulfur and rock particles straight into space. Gradually losing speed under the influence of gravity, the volcanic precipitation disperses over the surface of the satellite and then gently descends downwards. This is how the giant ring is formed, so clearly visible from space. Many of Io's volcanoes have similar formations, but the Pele ring is the largest. It is active volcanism that is the main reason for the formation of Io's special, unique atmosphere. According to available data, the atmosphere of the satellite is very thin and mainly consists of sulfur dioxide. At the same time, its density varies greatly from region to region. For example, in volcanic plumes, the gas pressure is 25 million times lower than on Earth. Away from eruptions, meanwhile, the atmospheric pressure on the day side of the celestial body is on average 1 billion times lower than the value we're accustomed to, and the night hemisphere of the satellite is almost in complete vacuum. The atmospheric density there is trillions of times lower than the Earth's. Also, despite the fact that Io's atmosphere is extremely rarefied, and the satellite has no magnetic field of its own, polar lights have been observed on Io. Charged cosmic particles, accelerating in Jupiter's magnetosphere, bombard the nearby satellite, causing a multicolored glow in its atmosphere. Interestingly, Io's auroras, unlike those on Earth, most often occur at the equator, as it is there that the particles flying along a tangential trajectory have to penetrate the thickest layer of the atmosphere. Meanwhile, our journey across the expanses of Io will continue in a northwestern direction. Gradually, the lava lake calms down and begins to be covered with a slowly solidifying solid layer again, until the next flooding cycle. Since water and carbon dioxide, crucial for supporting life as we know it, are practically non-existent on the surface of Io, this celestial body is considered unfavorable for biogenesis. However, the conditions on the surface of Loki Patra and other lava lakes, hypothetically, may be suitable for the origin of unusual life, resistant to high temperatures and obtaining energy from chemical reactions involving sulfur or iron. There are such creatures on Earth as well, that mostly live in the vents of underwater volcanoes or isolated oceanic caves. Still, due to Io's tectonic activity and extreme temperature variations on its surface, realistically, the probability of this phenomenon is rather low. Interestingly, it may be observed that although the uplands and volcanoes are the most remarkable features of Io's relief, they occupy a relatively small area. Tectonically active areas of the surface are separated by vast and relatively flat regions covered by a thick layer of sulfurous sediments. When viewed from space, these areas stand out with lighter colors, and the largest of them extend for thousands of kilometers. For example, if we head west from the Petroloki, passing numerous small volcanoes and lava flows, we will soon reach an area called Media Regio. It is a bright and relatively smooth, irregularly shaped area surrounded by mountains and large paterae. Its diameter is variously estimated to be about 2,600 kilometers, and its area accounts for about 12.6% of the satellite's total surface. While most of this region is uniform and smooth, in some places the plain is cut by lava flows associated with adjacent volcanoes. It is assumed that the lithosphere beneath Media Regio has an exceptional thickness, forming something reminiscent of the Earth's continents. That is the reason why such a large surface area has retained its integrity for a very long time. According to another hypothesis, the upper layers of the satellite's mantle are melted in fragments, and there is no liquid magma beneath the tectonically inactive plains. Observations show that in contrast to the volcanic regions, the plains of Io are characterized by a cold climate. With their dark color against the background of the light-colored plains around, they produce a stark contrast with their brightness. The largest of these flows extends northwards for more than 300 kilometers and is up to 60 kilometers wide. Thus, this feature is the largest active lava flow in the solar system. The second largest lava flow extends westwards for as much as about 250 kilometers. Previously, it was considered an independent formation, but more detailed images of the surface showed that this object is also part of Almirani. In addition, to the east of the main patera, there is a crown of small dark streams, the color of which suggests that they consist of silicates, which first melted and later solidified. Almirani has a complex internal structure. It is assumed that in addition to the main active area, there are magma tubes lying beneath the surface of the satellite in this region. Their occasional outbursts are the cause of eruptions outside the main rift. Observations in the infrared spectrum show that the main patera is heated to about 1900 Kelvin or 1630 degrees Celsius, and the temperature of individual hot spots surrounding it reaches 1200 Kelvin or 930 degrees Celsius. It is likely that this value is so high due to the fact that directly beneath the volcano there is an upward magma flow carrying molten matter from the lower mantle layers. There is also evidence suggesting that Almirani is likely a very young shield volcano. Over time, the lava it spews out will form a vast flat shield, hundreds of kilometers in diameter, and it is likely that this volcano will become similar to Olympus Mons on Mars. It is hardly disputable that in spite of its relatively small size, Io exhibits highly anomalous tectonic activity. In fact, because of its low mass, it does not have sufficient reserves of radioactive substances, the decay of which is the source of internal heat for most planets. It is believed that the reason for the abnormal activity of this celestial body is the tidal interaction with Jupiter. Combined with the orbital resonance that keeps Io in a stable orbit, the gas giant's attraction strongly heats up the satellite's interior and deforms its crust, and this causes frequent and powerful eruptions. Combined with low gravity, they become truly spectacular. every celestial body in the solar system is unique in its own way. Some are frozen in eternity, like the barren Mars, or else covered in ice, like Pluto, while others yet, like Venus or Titan, are enveloped in a thick atmosphere. However, there is a completely different world close to us. Its depths shudder with devastating internal cataclysms, and hundreds of bubbling volcanoes unpredictably lash out at the space around with massive emissions. A huge planet covers most of its sky, occasionally eclipsing the dim sun, and its vast valleys are painted in millions of yellow-red hues. Such is Io, Jupiter's satellite, dangerous and fierce, but at the same time so beautiful and marvelous. Today, Io is known to be one of the largest satellites in the entire solar system, second only to Ganymede, Titan and Callisto in size. Its radius is 1,821 kilometers, and its mass reaches about 8.9 times 10 to the power of 22 kilograms. If we compare this celestial body with the Moon, it turns out that these objects are almost identical in size. However, if we compare the masses, we will notice that Io is more massive than the main satellite of our planet by as much as 21%. This suggests that the average density of this space object is higher than that of any other satellite in the solar system. According to calculations, it is about 3.5 grams per cubic centimeter, which is noticeably higher than most non-metallic rocks. And to understand the reasons for the anomalous density of Io, we need to look deep into it. According to today's concepts about the structure of celestial bodies, Io has a relatively compact core at its center, made up of iron and sulfur. It accounts for about 20% of the satellite's mass, and its radius, according to different estimates, is between 350 and 900 kilometers. Calculations show that given such parameters, internal heat release will be insufficient to melt most of the core. This is also confirmed by the fact that this celestial body has almost no magnetic field of its own. Mathematical modeling shows that the satellite's core is surrounded by a solid mantle, at least 75% of which is made up of the magnesium-bearing mineral forsterite. According to calculations, its outer part is molten and forms an ocean of magma about 50 kilometers deep. Its temperature is about 1600 Kelvin, which is more than 1300 degrees Celsius. Moving on in a northwesterly direction, we will soon reach a gigantic chasm called Loki Patra. This formation is the largest volcanic depression on Io, with a diameter measuring roughly 250 kilometers. Thus, the total area of this great chasm exceeds 50,000 square kilometers, which is about 1.5 times larger than that of Lake Baikal, one of the most majestic lakes on our planet. However, unlike terrestrial bodies of water, this chasm is filled with hot sulfur silicate lava,